Hello everyone, I'm Dinshaw Balsara and I would like to use this talk to introduce you to alternative finite difference WENO schemes for conservative systems as well as hyperbolic systems with non-conservative products. This is part one of a two-part talk, and I split it out in two parts just to keep it manageable. I would like to begin by giving thanks to my esteemed collaborators without whom this talk would not be possible, and I'd like to go ahead and jump into this talk. So, the plan of the talk is that we will first begin by comparing and contrasting finite difference to schemes with finite volume schemes. Once that is done, we will actually go ahead and talk about finite difference WENO schemes and compare and contrast them with alternative finite difference WENO schemes. This will give us a chance to talk about reconstruction versus interpolation. We'll talk about the derivation of a very general purpose AFD, which stands for Alternative Finite Difference WENO scheme for conservation laws. Um, And we'll also use that as a chance to talk about the advantages of alternative finite difference WENO compared to classical finite difference WENO. And we'll end this part by showing the generality of the scheme for conservation laws. For the next part, we will actually go ahead and show how this extends to hyperbolic systems with non-conservative products. Um, and show the generality of the approach as it pertains to non-conservative products. We'll talk about general relativity as a test case, showing how these schemes can actually be applied to extreme circumstances, and we'll talk about conclusions and future work. So this part basically deals with the first half of this talk, and let's go ahead and launch it. So consider a finite volume scheme. What do? We have a PDE system, a conservation law as shown out here, and we take its space-time average. And that actually allows us to write the solution at time tn plus 1, which is this guy in the zone ij, in terms of the solution at time tn, which is this guy and shown out here. And basically, the space-time integration allows us to write it in terms of fluxes that develop at the boundaries of this space-time control volume that is shown out here. So the x flux contributes to this space-time phase, and the differentiation of that x flux in a space-time average sense is shown out here. The y flux likewise contributes to this space-time phase, and the differentiation of that is shown to you out here. Now, because we're dealing with all average terms, we're seeing the over bars on U bar and F bar and G bar. But this approach actually highlights the strengths as well as the weaknesses of the finite volume approaches. Namely, they're very expensive in terms of the multidimensional reconstruction that one has to carry out. And furthermore, the flux evaluation has to be done at space as well as in many cases space-time evaluations at quadrature points, and therefore one has multiple calls to the Riemann solvers, and that makes the approach very expensive. Of course, the approach is also very flexible because it ensures that the solution is available at all spatial points and even perhaps at all space-time points. And our concept of conservation is very natural and very evident. So those are the plus points of this approach. Let's go ahead and compare and contrast that with a finite difference approach for the same partial differential equation. Here we're trying to go ahead and obtain in the zone ij the solution at time tn plus 1, which is this guy, in terms of the solution obtained written at the center of the zone ij at time n. So these are point values of the solution at time tn plus 1 and at time tn, and the update is expressed in terms of the difference between the x fluxes evaluated at the right and left x phase, again in a pointwise sense, and the difference between the y fluxes again evaluated in a pointwise sense at the y faces and differenced out here. So notice that this approach is going to be very efficient in the sense that if there is any interpolation, it will be done in a dimension by dimension fashion, which is very inexpensive. There's only one call to the Riemann solver per phase per fractional time step. The flip side is that it's not as flexible in the sense that you don't have a space-time interpretation of your solution, and the concept of conservation is only expressed in a differential sense, which might be inadequate in certain applications. So with that, let's go ahead and move forward. Let's go ahead and do a quick compare and contrast between the classical finite difference we know as we know it, which is the one that reconstructs on the fluxes, and the new alternative finite difference we know as we will actually be introduced to it. Our goal in this section is not to develop the alternative finite difference we know, but just show the difficulties that might come up in developing such an approach if we're not very careful. So let's go ahead and first focus on the the classical flux reconstruction based finite difference we know, which actually originates from this paper and of course subsequent papers that follow from it. And we want to actually make a pointwise finite difference style update of this equation, which basically means that if we want to make an accurate update of the time derivative, we will need the accurate spatial derivative up to a certain high order. So if we go ahead and discretize the system like this, then this right hand side has to be a very accurate representation of d by dx of f evaluated in a pointwise sense at the point I in the zone I. So with this, we actually realize that we have to find a strategy to achieve this goal. And the strategy that was used in Shu and Osher 1989 was to basically say, imagine that you have a function curly f out here, and you want to average this function curly f from x minus delta x over 2 to x plus delta x over 2. So you want to average it in space, and you want to call the result little f. Now, of course, these curly f and little f are abstractions at this present point, and there's no need to try and relate them to the flux, but we will see how that relationship develops in a very, very short amount of time. So with that, if we use or if we apply the fundamental theorem of integral calculus to this equation and differentiate with respect to x, then we realize that the spatial derivative of f of little f is just a finite difference like looking form for curly f. And this gives us our clue. So we actually realize that this could be a very accurate procedure if curly f out here, this guy and this guy, is a good representation of this guy and this guy out here. So how do we obtain such a good representation? The answer is that we go back to our knowledge of reconstruction by primitive and say that f integrated over the zones should be such as to be equal to the zone averaged value of the actual flux. So this is our philosophy of reconstruction by primitive, and we realize that if this reconstruction by primitive is applied to the fluxes themselves, to the zone-centered fluxes themselves, then we will get an accurate approach. So that's the idea, that's the first essential idea that is followed in classical flux reconstruction based finite difference we know. The second important idea embedded in that is to actually go ahead and split the flux into, so if this is the flux, it is split into a right going part of the flux and a left going part of the flux, and this right going part of the flux is denoted by f plus. So you see that f plus is just this guy out here, and F minus, the left going part of the flux, which is just this guy out here. To make F plus purely right going and F minus purely left going, one has to choose an extremal speed, which is that S must be greater than or equal to the spectral radius of the Jacobian being considered for the flux. With this, we actually go ahead and realize that in order to actually obtain upwinding, F plus must be built from stencils that cover the zone I when evaluating F plus at the zone boundary I plus a half, which is this zone boundary out here. Likewise, F minus at the same zone boundary must be built from any stencils that cover the zone I plus 1. So we realize that this scheme necessarily will need a reconstruction of the fluxes, a reconstruction by primitive of the fluxes, but it will need a reconstruction by primitive of the fluxes going to the right, and it will need another yet reconstruction by primitives of the fluxes going to the left. And since these will have to be done in characteristic space, we will need two characteristic projections to basically build such a scheme. Okay, so the scheme out here is definitely very popular, very well loved by everyone, but it still has, despite its many strengths, it still has some weaknesses. One of the weaknesses is that the numerical flux is not obtained as a point value, but rather as a reconstruction of the flux. And the consequence of that is that it actually limits the types of Riemann solvers that can be used in finite difference WENO schemes. And the other consideration that we pointed to is that you have two fully characteristic reconstructions, and we would actually like to get by with just one characteristic reconstruction if we could. Okay, one characteristic reconstruction per dimension instead of two characteristic reconstructions per dimension. So now let's go ahead and get our first introduction to the alternative finite difference WENO approaches. And we're not going to derive the method in this section. That we will do in the next section indeed. But what we're going to do is we're going to basically retrace some of the development of this idea and understand why a naive approach to developing an alternative finite difference WENO will be limited in its accuracy. So these methods were initially presented in Shu and Osher 1988. So they predate the well-loved scheme. And unfortunately, they were not widely understood, nor was this method slow. This method was kind of slow in arriving at its maturity. But it does have very numerous strong points, which I would like to point out at the end of the next section. So let's go ahead and imagine that we take a naive approach to obtaining higher order. We start with a mesh function, which is defined in a pointwise fashion at the centers of the mesh. So you can see that out here, zones I minus 2 all the way up to I plus 2 in this figure out here have a mesh function that is defined in a pointwise sense at the zone centers of these meshes. And we're assuming that we have uniform meshes. So we can actually go ahead and do higher order interpolation. Notice interpolation is different from reconstruction. Reconstruction by primitives just works on the zone averages, whereas interpolation makes sure that you actually match the point values over all the zones that contribute to that particular stencil. So with that, let's say that we do a higher order interpolation and we're interested in this zone boundary I plus a half. Okay, then from the left of I plus a half, we have an interpolant, which is this guy. And from the right boundary of this same zone boundary, we have a right interpolant, which is this guy. And let's say that we have a reasonably good or a very good Riemann solver. So we throw in both the left state and the right state into the Riemann solver and obtain a resolved flux. And then, because we want to discretize this guy, let's say we naively obtain this discretization. The problem is that this discretization will only be second order, as we will see in the next transition. So here's the fundamental issue. We start with a mesh function that is defined as point values at the zone centers of each mesh. We're doing finite difference, so we go ahead and do a higher order interpolation in each dimension, and we go ahead and obtain two interpolated values at each zone boundary. Here we're considering the zone boundary I plus a half. We obtain a left state from the left side of it, and we obtain a right state from the right side of it. We pass it on to a Riemann solver, and we make a naive finite differencing of it. What could be wrong? What we realize is that this is only going to give us a good second order scheme. In other words, it's the finite differencing of these fluxes that causes a degradation in their order. In other words, realize that this guy was higher order accurate, this guy was higher order accurate. When you dump them into the fluxes, you got a flux that was higher order accurate at the zone boundary I plus a half. You put that flux in here, you did similar operations to get a very high order flux out here, but when you finite difference them, you did not get a higher order accurate representation of df by dx. Instead, you got only a second order accurate representation of it. Let's go ahead and assume that you have a very smooth flux function, and let's do a Taylor analysis around the zone center x is equal to 0. So we have f0 defined at that zone center, we have the first derivative defined at that zone center, we have the second derivative defined at the zone center, we have the third derivative at the zone center, and let's then go ahead and evaluate this Taylor series expansion at the zone boundaries x is equal to plus delta x over 2 and x is equal to minus delta x over 2, which is what we've done out here. When we go ahead and finite difference it, we realize that we have a central value which is exactly the one that we want, namely a gradient of f, but we realize that we have a delta x squared over 24 times the third derivative of f, again evaluated at that point. So we realize that because of the delta x squared, we're clearly stuck with having only a second order scheme. So in other words, we realize the tremendous value of this idea out here, which is to say that it's the finite differencing of the higher order boundary fluxes. Each of the boundary fluxes is pointwise higher order at the boundary that it is evaluated at. But when we finite difference it, we actually get a degradation of the order. So with that, we actually have an ability to do a little bit of compare and contrast, which is to say that the finite difference we know is actually doing reconstruction on the flux variables themselves. It's doing reconstruction by primitive on the flux variables themselves, which is to say that the reconstruction is the task of matching the zone average flux values in an integral sense. On the other hand, the alternative finite difference we know is starting with the point values of the solution vector itself, and it's doing an interpolation in the zone I and the zone I plus a half, or in the zone I and the zone I plus 1, in order to obtain the interpolants at the zone boundary I plus a half from the left and from the right. Now, interpolation is the task of matching point values at the zone centers in a stencil. So there's a fundamental difference between reconstruction and interpolation, which is essential for understanding what is to come subsequently. So finite difference we know reconstructs the fluxes in a finite volume sense. Alternative finite difference we know will do interpolation, pointwise interpolation of the zone center point values. With that, let's go ahead and now we're ready to jump into our derivation of the finite difference we know. Okay, so let's go ahead and do exactly that. Sorry about that interruption. So let's go ahead and realize that we have a Taylor series expansion of the flux. Just as before, we can assume that it's as smooth as possible, and we evaluate that flux at the x is equal to delta x over 2 and x is equal to minus delta x over 2 zone boundaries. We can also, for good measure, evaluate the first derivative of that flux, the second derivative of the flux, and so on and so forth. Now, let's go ahead and just do a simple finite differencing between the flux that we've evaluated at x is equal to delta x over 2 and the flux that we've evaluated at x is equal to minus delta x over 2. We see that we get the desired term that we want, namely the first derivative of the flux, but we also get an undesired term, namely we get an additional contribution which is plus delta x squared over 24 times the third derivative of the flux. Clearly, it's this guy, this additional term, that is throwing off our accuracy. Now realize that obtaining a third derivative at a zone center is equivalent to finite differencing two second derivatives which are defined at each of the two zone boundaries of that zone. So with that insight, we realize that we want to cancel off a plus delta x squared over 24 times third derivative. So we put a minus delta x squared over 24 times the second derivative at each of the right and left zone boundaries of the zone I that we're considering. And if we go ahead and take this guy to be our numerical flux, then the resolution is that when we go ahead and put this guy and we try to finite difference that, then this additional term, this new term that we've put in, will exactly cancel off this term which we found to be undesirable and which we wanted to get rid of. So we realize that including higher order derivatives at the zone boundary can actually allow us to obtain a higher order finite difference approximation at the zone center. So this is our important insight. Now we've only shown this for a third order scheme. Let's go ahead and ask if this insight can be generalized to all orders. In other words, what we're doing is rendering in Mathematica the same insights that Merriman had to obtain analytically. So let's go ahead and start with the Taylor series. Now we're going to demonstrate this at fifth order. So let's go ahead and start with the Taylor series expansion of the flux. Assume the flux to be as smooth as desired. Here's your Taylor series. Here's your value of the flux at the zone center. Here's your value of the first derivative of the flux at the zone center. Here's your value of the second derivative of the flux at the zone center. Here's your value of the third derivative of the flux at the zone center. Here's the fourth derivative, and here's the fifth derivative. And you can recognize that you have x squared over 2 factorial, x cubed over 3 factorial, x raised to 4 over 4 factorial, and x raised to 5 over 5 factorial flanking those derivatives. So with that, we can actually go ahead and evaluate our higher order derivatives at x is equal to plus delta x over 2, which is what we have done out here. So we just asked Mathematica to do all the hard work. Likewise, we can evaluate all our higher order derivatives at x is equal to minus delta x over 2. Now realize that here we're, just to keep things simple, we're taking delta x to be unity. Okay? And then instead of using a lot of mathematical moxie, let's just go ahead and make Mathematica use its mathematical moxie. So we'll go ahead and say that the flux at zone boundary x is equal to delta x over 2 is just the value of the flux evaluated at the zone boundary plus a times the first derivative of that same flux plus b times the second derivative of that same flux plus c times the third derivative of the same flux, plus d times the fourth derivative of the same flux, plus e times the fifth derivative of the same flux. And we do exactly the same thing at zone boundary x is equal to minus delta x over 2. Now, if we go ahead and finite difference the flux at x is equal to delta x over 2 from the flux at x is equal to minus delta x over 2, we find that the first term that we get is exactly right. So that coefficient comes out to be unity, which is exactly what we desire. But we want all the higher order terms to sequentially cancel themselves at the zone center, which basically means that we can set a whole bunch of conditions that have to be fulfilled by these coefficients a, b, c, d, and e. And we can get those coefficients explicitly spat out by Mathematica. So we get those coefficients and we see that the flux at zone boundary I plus a half is just the value of the flux evaluated at that zone boundary minus 1 over 24 times the second derivative plus 7 over 5760 times the fourth derivative. Likewise for the flux at zone boundary I minus a half. And so we see that these fluxes with these very special coefficients will manage to cancel off all the higher order derivative terms that accumulate at the zone center and just give us a very accurate representation of df by dx evaluated pointwise at the zone center. This is an insight that is very good because it actually tells us that we can continue this process onwards at any order that we desire. So we can actually now go ahead and obtain a third order numerical flux, and here's our familiar minus 1 over 24 times delta x squared times the second derivative at the zone boundary. But we can also obtain numerical fluxes. So this numerical flux at third order is made up of the actual flux from the Riemann solver plus an extra higher order contribution from the second derivative. If we want a fifth order scheme, we have again the flux from the Riemann solver, extra term that is second derivative term, and extra term that is fourth derivative term. Notice that now the second derivative and fourth derivative terms will have to be evaluated with higher order accuracy. Likewise, if we go to the seventh order scheme, we have the flux from the Riemann solver, additional contribution from the second derivative, fourth derivative, and sixth derivative terms. And those three derivative terms will have to be evaluated again with an appropriate higher order accuracy. Likewise, for the ninth order numerical flux, we get the flux from the Riemann solver, second derivative term, fourth derivative term, sixth derivative term for the flux, and eighth derivative term for the flux. And we'll keep this coloring scheme consistent all the way through, namely the additional terms for third order are shown as black, the additional terms for fifth order are shown as red, the additional terms for seventh order are shown as blue, and the additional terms for ninth order are shown as magenta. So with this, we have actually an AFD-WENO scheme for conservation laws, which is this guy out here, which is formally high order accurate. However, notice that at the zone boundaries, we have these higher order derivative terms. These higher order derivative terms are essential if we want the high accuracy to be preserved. But when the solution is smooth, we indeed should get that high order accuracy. When the solution is non-smooth though, just a simple finite differencing of these higher order derivative terms will actually lead to a Gibbs phenomenon, and that could be deadly for the quality of solution of a numerical scheme. So that's the challenge that we face. So we have essentially a numerical scheme for an alternative finite difference WENO based numerical scheme for our conservation law. Notice that the terms above this dashed line out here are actually the terms that give us just a very high quality second order scheme, but the additional terms are necessary for for giving us a higher order scheme. However, they have the potential to kind of give us oscillations also. Now notice that I can take this second derivative of f, or this fourth derivative of f, and write d by dx of f as a times du by x, which actually allows me to get a first derivative of a times du by dx at the zone boundary, likewise a third derivative of a times du by dx at the zone boundary. This is just a nicety. It basically simplifies the interpolation step that we have to do later on. So this is just saying that, okay, this makes the scheme a little more efficient if we recast it that way. So with that, we have to essentially now face up to the Gibbs phenomenon. Notice that when the solution is smooth, we absolutely need to retain these higher order derivative terms for the fluxes or for a times du by dx at the zone boundaries. On the other hand, when the solution is non-smooth, these higher order derivative terms can actually throw off our solution by giving us a Gibbs phenomenon. And There's an efficiency associated with writing things as A times du by dx. You might see it in the paper. It's very well described. And this gives us we need a very general purpose strategy for suppressing the Gibbs phenomenon when we don't need it. And this is where the WENO steps in again and gives us a strategy for curing the phenomenon. So think of WENO as a gift that keeps on giving, and we will use this WENO interpolation. We will use a new, differently designed WENO interpolation to suppress this Gibbs phenomenon. So how are we going to do it? The answer is that at each zone center, we have an interpolation going on, and therefore at each zone center, we can evaluate d by dx of u, which is the interpolant at that zone center. So at each of these zone centers, you're seeing that we're evaluating a times d by dx of u at this zone center, 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 and at this zone center. So the characteristic matrix A can also be evaluated using the point values, and d by dx of u can be evaluated, and therefore A times d by dx of u can be evaluated. And then we have essentially an interpolation strategy. So this is an interpolation strategy that relies on a large smooth stencil when the solution is smooth to give us very high accuracy representation of d by dx of A times du by dx and the third derivative of the same entity at the zone boundary of interest out here. Okay, because we're using WENO, we will actually go ahead and suppress spurious oscillations when they're present. And when they're not present, the WENO will actually give us a very high quality representation of these higher derivatives that we want to see evaluated at the zone boundary. So this is going to be our strategy, and pictorially, the entire WENO scheme can actually be represented as saying that we first do a WENO interpolation. This interpolation will have to be done in characteristic space, but there's only one interpolation per zone, which is a bonus. And then at each zone boundary, say I plus a half, we will obtain u minus I plus a half from the left of that zone boundary, and u plus I plus a half from the right of that zone boundary. We stick those into our flux term, our Riemann solver, and we get a result flux. And if we just retain the first row of the WENO scheme that you saw, you will actually get a very good second order scheme. And if we retain the higher order gradients, we will get an improvement. So at each zone center, we actually evaluate the gradients of our interpolant. And once we evaluated the gradients of our interpolant, we can actually evaluate the characteristic matrix also and construct A times du by dx at each zone center. And then we go ahead and use another WENO interpolation to interpolate the higher order derivatives of A times du by dx at the zone boundary of interest. And the important thing is that for this evaluation, we do not need to use characteristic decomposition. So that makes the scheme very much more efficient, because dispensing with characteristic decomposition gives us a much more efficient scheme. So with this, we can do a little bit of compare and contrast. On the left-hand side, you see the classical flux reconstruction-based WENO scheme. On the right-hand side, you see the new alternative finite difference WENO scheme. Notice that the classical WENO scheme is locked because of our use of the fundamental theorem of integral calculus. It is locked to a certain very narrowly defined set of Riemann solvers. On the right-hand side, you can use any type of Riemann solver. For example, if you need to retain a stationary contact, you can have a Riemann solver that has that property of retaining stationary contacts. Because F plus and F minus are reconstructed, you do not have free stream preservation out here, whereas by design you can actually obtain free stream preservation out here for alternative finite difference WENO schemes. WENO reconstruction is well known and it is oscillation free. WENO interpolation has been invented and documented very thoroughly in the papers by now, and this basically gives us control over the oscillations stemming from the Gibbs phenomenon. Well balancing is obtained for both approaches. Treatment of stiff source terms is obtained for both approaches. For flux reconstruction based approaches, there is a fluctuation form that is available. On the other hand, for PDEs that have non-conservative products, we will see in the next part that we have a flux conservative form that can still be applied to the rest of a PDE system. If part of the PDE system is in conservation form and the other part is not, then the parts that are in conservation form will indeed be preserved in conservation form by the AFD-WENO approaches. And so that's a very strong positive. Now, why is this method known as alternative finite difference WENO? It was first initiated in Shu and Osher 1988. Was not very usable or comprehensible at that time, and it was basically superseded by an extremely popular approach that came a year down the road, and this was the flux reconstruction based finite difference WENO. It had a slight finite difference ENO, and it had the slight problem that it had very rapid stencil switching, but via this paper and this paper, that issue was resolved, and it was also shown that higher order approaches were very easy to achieve. Now, the first breakthrough that came was Merriman in Journal of Scientific Computing was writing in honor of Osher's 60th birthday, and he published a paper basically simplifying and illustrating why this method should indeed work. The real impetus for developing this method came from these two groups, who basically showed that the classical flux reconstruction based WENO could not preserve free stream condition. And therefore, that forced people to actually pay attention again to alternative finite difference WENO. So the alternative finite difference WENO was invented because it is truly an alternative to the flux reconstruction based WENO or ENO methods. There's still the deficiency, even in more recent papers, of treating the higher order flux derivatives at the zone boundaries without engendering Gibbs phenomenon, but that was resolved via this paper out here by the invention of different styles of WENO interpolation. And with that, we basically complete our description of the WENO scheme, but now let's go ahead and show how general purpose it is by applying it to the Euler equations and also the 10-moment rarefied gas equations and also the equations of relativistic hydrodynamics. In each instance, our time stepping will be very standard SSP RK3 or RK4 approaches, or if there are stiff source terms, we will use the IMEX approaches from Peresci and Russo. So with that, we basically see that for the hydrodynamical vortex, we have a very good solution out here where each WENO scheme at each order preserves its order of accuracy. We can also see that for the 10-moment rarefied gas flow, we have again the scheme meeting its order of accuracy. We can see that for relativistic hydrodynamics problems, the schemes meet their order of accuracy again on an isentropic vortex type problem that has been constructed. We can see that for Euler flow, all the shocks that should be captured crisply are captured crisply, and of course the vortex roll-up is also shown very nicely out here. We can also see that for the 10-moment rarefied gas flow problem, for flow situations, we have a uniform density to begin with, and we allow for the velocities to kind of at supersonic speeds flow outwards, and we can actually see that Pxx, the xx moment of the pressure, Pxy, the xy moment of the pressure, and the Pyy, the yy moment of the pressure are properly represented out here. And this actually, and then you see a problem with relativistic hydrodynamics, and this is a dense parcel of gas which is hit by a shock, and you can see this parcel of gas rolling up, or actually it's a light parcel of gas, light spherical parcel of gas that's been hit by a strong shock, and you can see it rolling up, and you can actually go ahead and see that going from third order to fifth order, there's a marked improvement in the features that are captured. And as you go from fifth to seventh order also, you see substantially better treatment of the vortex roll-up. And with this, we've completed the first part of this conversation, and I look forward to seeing you in the second part. Thank you very much. Talk to you soon. Bye bye.